So in this video, we're going to look at permutations, and we're going to start off by defining what a permutation is. We'll come up with the NPR formula, and then we'll look at it some more, see some abstract and see some applied problems where permutations play a role. So let's start off with the definition. So a permutation is a way to order or arrange some elements or objects or whatever the problem is ordering or rearranging. So in the previous videos when I said how many ways are there to arrange the letters A, B, C, each of those arrangements is a permutation of A, B, C. So B, A, C is one permutation of the letters A, B, and C. The most common problems we're going to see is talking about the number of permutations, and the number of permutations is equal to the number of distinct orders or arrangements. So from our example earlier, when I said how many ways are there to arrange the letters A, B, C, that's the same thing as saying how many ways are there to permute the letters A, B, and C, and there are 6 ways. Alright. NPR. Now, when I see this here measures the way or the number of permutations of R elements from a total of n elements. And the formula NPR is n factorial divided by n minus r factorial. Now I'm going to start off by explaining this numerically, and then I'll get back into this a little bit algebraically, but not too deep because it gets a little bit messy. So let's consider an example we saw in the last lesson about 8 people in a race and finding a first, second, and third place finisher. That is the same thing as valuing 8p3. So in here we have 3 people we care about, and 5 that we don't. And so when no one's finished, there are 8 possible first finishers. After one person is finished, there are 7. After the first 2 have finished, there are 6. That's all we really care about. These still finish, so 5 choices for the 4th person, 4 for the 5th, 3, 2, and 1. But the thing is, we only are looking for how to arrange the first 3. We don't ever actually multiply through the rest of this. The rest of this is sort of canceling out. So 8p3 is the same thing as 8 times 7 times 6, which is 8 times 7, 56, times 6, 336. If you're doing this work by hand, it's probably fastest to just sort of think it through this way. You don't really need to make these little spaces to fill in. You can just say, okay, well, I start with 8, 7, 6. I have 3 of these numbers here. Let's see how the formula does this same thing. So in the formula, we know that 8p3 is going to be 8 factorial divided by 8 minus 3 factorial 8 factorial is 8 times 7 times 6 times 5. That's 4, 3, 2, and 1. 8 minus 3 is 5. 5 factorial is 5 times 4 times 3 times 2 times 1. And the 5 factorials top and bottom cancel. And as before, we're just left with 8 times 7 times 6. And so this same thing, the same idea works algebraically where, and I'm not going to get too deep into this, but this means I'm going to end up with R spots to fill and then get rid of everything else. So we start off with n. This will be 1 less than n, 2 less than n. This, if I have r elements, I only need to subtract r. I only need to subtract 1 r minus 1 times. So I have 1, 2, 3. So this is actually going to be n minus r plus 1, the number in here. And then the useless, the junk, the stuff we don't care about here, ends up giving me 1 fewer than this, which is just the n minus r factorial. And same thing that happens here. We use this to cancel out everything that we don't care about in this problem. Okay. Let's look at a couple abstract problems, and I'll also show you how it can be put into the calculator with some numerical problems based on this. So the number of ways to permute 0 objects out of n objects, well, if you think that through, if I'm not moving any objects, there's got to be just one way to do it. And the formula works the same way. So I do n factorial divided by n minus 0 factorial, which just ends up being n factorial over n factorial 1. If I have n objects and I'm permuting one of them, that's basically choosing one thing out of n possible things, and there should be n ways to do that, and that is true. So we would end up with n factorial divided by n minus 1 factorial. And as we saw last lesson with factorials, when I have these two factorials, there's one more term in this top factorial, because it's n is 1 bigger than n minus 1, so the top is the same thing as n times n minus 1 factorial. The bottom is still n minus 1 factorial. We can see that the n minus 1 factorials cancel, and we're left with just n. Final example here, if I have n objects and I'm permuting all of them, that's the same thing as just sort of ordering n objects. That's just factorial. And this helps explain why we really love 0 factorial to be 1. So by the formula, npn should be n factorial divided by n minus n factorial. And n minus n is 0. Since we defined 0 factorial as 1, we just end up with n factorial. Whereas if we had tried to define 0 factorial as 0 for some odd reason, we would get an undefined thing, and our NPR formula would have to have special cases in it. We'd have to deal with different things differently instead of just having one formula that works for everything. Now, before we move on, let's see some numerical examples of these and see how to put in the calculator. So let's consider 5p0, 5p1, and 5p5 and see if we get what we expect. So we expect this to be 1, we expect this to be 5, and we expect this to be 5 factorial, which is 120. And of course, I could put this into the whole formula like we did the last slide, but let's see how the calculator works for this. So for the TI calculators, it works pretty much the same, even the scientific calculators. The other calculators work similarly. I just start off by typing the first number in, so I get 5. And then I go to Math, over to PRB, and you see NPR 1. And 5 permute 1 gives me 5 here. If I did 5 permute 0, I did it in the wrong order. Sorry about that. 5 math PRB, it's the second one in the list. 0. And finally, 5P5, so 5 NPR 5, and I should get 5 factorial, which is 120. Okay. So, let's look at a problem here. The senior class at a certain high school consists of 100 students. In how many ways can a class president and a class vice president be elected? And the real important thing with these permutations is there's a difference between the first and second. There's an order to them. I have 100 total students. I'm permuting 2 of them, so that's the same thing as 100 P2. I can put it in the calculator, or this is simple enough I can do it by hand. So 100 P2 is going to end up being 100 factorial divided by, and I'll write it out here, but you can obviously go straight to 98 factorial, which is going to be 100 times 99. We have first spot, second spot, which is 9,900. Okay. Sometimes we're going to permute things where there's more than one element in here that's repeated, that's indecipherable from one another. And what we can do when we're trying to permute those is you are going to first permute all elements, and then second, you can divide by the permutations of repeated elements. So another way to look at this, if I permute all the elements, if there are n things in there, that's going to be n factorial. And then if each of the elements, or each of the distinct elements, is repeated sort of k sub I times, you can divide out by those. So it's going to end up being equal to n factorial divided by all of these repeated things multiplied together. Okay, so what I mean by this is the following. Let's consider common example, ball. If I'm not smart about how I do this, I'll look and see that there are 4 letters, and I'll think that it's going to be, so equal, I'll put a question mark up here, 4 factorial, 4 times 3 times 2 times 1, 24. But when I start to try to list off the ways to do this, I'm not going to be able to get all the way up to 24. And here's why. I really have 2 things that are the same. I have this L, and I have this L. So I'm going to try to list off everything, and I'm going to, for purposes of this, label these L1 and L2, but then we'll see how many different things we have, and I'll show you how this formula works. So I could have BA L1 L2, I could have BA L2 L1. I could have B L1 A L2. I could have B L1 L2 A. And I could have, let me see, B L2 A L1, B L2 L1 A. Now, I'm going to put some ellipses here. I'll explain what's going on in a second. This is every permutation that has a b at the front. You can try to find another one, you won't be able to find them. And I had 4 possible things to start with, so this covered all the b's. Then I'm going to have the same type of thing for all the a's, same type of thing for all the L1 starting off with, and same type of thing for the L2 starting off with that. But what we see is this. If I don't somehow differentiate between L1 and L2, then these are the same, and these are the same, and these are the same. And that's because in any single permutation of ball, there are, since there are 2 L's, 2 factorial ways to move the L's around. And so each, if I try to count 24, each of those shows up too many times. 2, it shows up twice. Maybe 1 too many times, it shows up twice. So instead of just doing 4 factorial, I should have 4 factorial and divide that by 2, or because it's 2 factorial ways to do it, which is going to give me 12 actual distinct ways to rearrange. And if you try to list them all off, you will not be able to get more than 12 unless you somehow differentiate between this first L and the second L. I've also seen people do like a lowercase l and uppercase L. And the formula is this. So using the formula, we had 4 total things, that's n. So I have 4 factorial up there. And I can just say, okay, these are repeated, so I'm going to do 2 factorial. Now, based on the formula, I could include the b and the a, but I don't need to because there's only one b. 1 factorial is 1. It's not going to change things. And there's only one a. 1 factorial is 1. It's still not going to change things when divided. And so that's how I get there. So 4 factorial 24, 2 factorial 2, 24 divided by 2 is 12. I do want to point out this formula still works when I don't have anything that's repeated more than once. If I consider math here, there are 4 elements, so 4 factorial, and I can say, okay, there's 1m, 1 factorial, there's 1a, 1 factorial, there's 1t, 1 factorial, there's 1h, 1 factorial, multiply those all the way through, and you'll end up with 24 over 1, which is just 24, what we saw earlier when we only had factorial. So let's look at the example that everyone loves to do, Mississippi. In Mississippi, there are 11 letters. So I have 11 factorial. And a bunch of repeats. So m only appears once. I could put a 1 factorial. I don't need to. I repeats itself 4 times, so I have 4 factorial for the i's. S repeats itself 4 times, 4 factorial for the s. P repeats itself twice, 2 factorial for the p's. It's also worth noting I could consider z's. There are 0 z's in here, and I could include a 0 factorial. 0 factorial is also 1. It doesn't change my answer. When I go through this, do the 11 factorial first, do all of this, and then divide. Be careful typing into the calculator. You would want parentheses if your calculator doesn't show it like this. And when you get through there, you end up with 34,650 ways to permute the letters in Mississippi. Last idea here, and we'll see an example of this, permutations with extra requirements. And what I mean by extra requirements is I can say, okay, how many ways can I permute something but keep these 2 things together? Or I want to have this group together and this group together, but permute everything else. There can be other things, but I'm going to focus on that for this right now. So basically, the first thing I'm going to do here is consider groups as a single element. And find the number of those permutations And then, once I've done that, I'm going to go ahead and multiply by the ways to permute each group. So here's an example. We have Jack and Jill, they're apparently best friends. I want to figure out in how many ways I can order 5 students, line them up, but I want to make sure that Jack and Jill are next to each other. So here's the idea. Instead of starting off by considering all 5, I'll say, okay, we'll consider that I'll have Jack and Jill together and these other 3. And now there are 4 things that I'm permuting, so I can do that 4 factorial ways. So this is permuting with Jack and Jill as a group. And then finally, I need to figure out how many ways Jack and Jill can rearrange themselves. There are only 2 people here, so that's 2 factorial. So I can multiply this by 2 factorial. And this is the way the permutations in the group, because I can each spot that I have Jack and Jill in this, I can have them in the order Jack Jill or in the order Jill Jack. I could include these, but they're only sort of groups of 1, so including 1 factorial for Jane, 1 factorial for Jim, and 1 factorial for John doesn't change anything, so I'm not going to write them out, but you could. 4 factorial is 24, 2 factorial is 2, and that's going to end up giving me 48 possible permutations where Jack and Jill are standing next to each other, or next to each other in the group in either order. Okay, next video up will be some practice problems for these.